the competing definitions are?
The biggest distinction is sometimes in mathematics, when they say a smooth function, they mean C infinity, infinitely differentiable. Whereas usually when I say smooth, I just mean C1. So it's just a smoothly differentiable function one time.
Okay.
And then, yeah, and then of course, some people think of anything that's not like L2 as being smooth. I don't know, just there's a lot of different ways of thinking about these function spaces. But normally the idea of smoothness, I think it's pretty universally considered to be the CK spaces, K greater than or equal to 1.
Okay.
So let me just ask a question about.
Oh, sorry. Go ahead.
I just wanted to just ask a high-level question about the experience that the students who are enrolled or maybe not enrolled, but doing the homework and following along closely. Most of you are engineers. I'm curious how it's been to be exposed to all these new mathematical ideas, how that's going. The notes are helping. Anyway, just.
I think for me personally, it was a steep first week, really steep learning curve. But now it's like, now that I put in the time, it's become a lot easier to kind of read through the notation and understand what it's saying, and also see new connections.
Yeah, that's not bad. 1 week.
Yeah.
Good.
So I would second on the steep learning curve, but I haven't gotten through the notation yet, so still working on that.
Okay.
From industry, I find that it is a steep learning curve for the math, and I haven't had the time to work through it. I put in 8 hours and couldn't put any extra time than that, so still looking into it.
Well, that's pretty good, Eric, that you're able to find 8 hours.
Yeah, I kind of, I made some other projects wait.
Yeah.
This is Lindsey, and my background is in mathematics, and what I found is that I'm able to understand the notation, but it's been really valuable to get an engineering perspective that you've been giving and relating those back to practical problems. That's something that I never got in my formal classes before, and it's been really rewarding and interesting to be able to make that connection for me.
Yeah, I really am trying to add those insights, because a lot of those are hard earned, because they're, like you say, it's like hard to find. It's just hard to find that, like those relationships anywhere, really. Okay, good. So for those of you who are working through the problems, there have been a couple of good questions. I've updated a few of the problems to make them a little more straightforward or a little simpler. So I appreciate that feedback. I'm making these up as we go, so I'm not going to hold you guys to kind of a ridiculous schedule. I think what we'll do is I'm going to have due dates for all of the assignments, but I'm not going to enforce any kind of late submission policy, so you can submit them anytime you want. The fact of the matter, in this course, we have people from math, physics, and several different engineering disciplines. So I'd prefer that you have an opportunity to go at whatever pace. You're all beginning from different starting points. So as long as, I mean, the only hard deadline, I guess, is going to be the last day of finals. My recommendation would be that you do not want to succumb to procrastination, or else you'll just never, you won't be prepared to learn when the topics are introduced. And so that would be kind of a shame to miss out on that. But so that's going to be the approach. So I'm not giving you material that's perfect either. And so there's going to be a lot of back and forth this semester. Okay, any other questions on homework?
Yeah, I had one for number 9, and it was specifically relating the Schwartz inequality to the, oh, what's the term called? So it's relating the Schwartz inequality to the triangle inequality for the semi-norms.
Okay, yeah. Let me pull up the problems. So I'd like to give you guys an opportunity to help one another. Has anybody finished that problem?
No.
I did it, but I don't know if I just took too big a step, because I'm not sure exactly if an equation that I used to prove that they're equal actually holds. So that's kind of where I'm at.
If you do it right, it's really obvious you did it.
Okay.
It's not a subtle thing. It just comes out of an algebraic manipulation. So let me give you a hint.
Okay.
Start with something like, let's see. Can you guys see my screen?
Yep.
Okay, so we're on 9, and the question is about Schwartz. So you start by saying, you say U plus some V, U plus V, and then you multiply everything out. U plus 2UV plus VV, and then, well, I don't want to say any more than this. Then you apply Cauchy-Schwarz here, and then you're done.
Okay, that makes a lot more sense. I was thinking it was, yeah, I didn't do it that way. So you, instead of having it just be U, you do the U plus V as the variable place.
Yeah, so it's
Okay.
not like a direct line reasoning. You kind of work backwards in a way.
Gotcha. Perfect. That helps a lot. Thank you.
Sorry, can you repeat what that CS stood for? You say Cauchy-Schwarz or something like that?
Cauchy-Schwarz, yeah, because once you're here, you can now say that this is less than or equal to U V, and then remember anyway that this is the inner product squared, right? So you basically have the triangle inequality multiplied out here is what this ends up showing you.
Thank you.
Okay, good question. I'm curious, this I actually kind of like this problem. This one went through a couple of evolutions. Does anybody have any plots that they can show here?
That was actually a question of mine. I wasn't entirely sure as to what exactly we were supposed to plot against the error.
So I got a couple plots of this. I plotted the sign and then the, I don't know what you're calling the sign with a subscript H. But I plotted both of those and then tried to get the error. But when I'm working through that problem, I I don't know, getting a straight line at the end of the day. I don't know if what I'm supposed to be getting. I could show what I have, but
Well, let me just at a high level, let me talk about this, and then we can take a look. This problem's kind of interesting because in a way it's like a little teeny simple finite element method where you're taking some analytic function, the sine function, and then we're building an approximation, right? This is the first 3 terms of the Taylor series expansion. So if you think about the sine function, it comes up. And so we're going from 0 to 1. And you can see that this function here, it's not a line. It has a little bit of curve to it. And so you can see that a linear will give you that approximation. But then if you add a quadratic to it, it gives a little bit of, and in fact, it's or a cubic, a negative cubic, right? So then it gives it a little bit of bend, and then there's a little more bend with the 5th. And so when you add these together, it gets closer and closer to looking like the sine function. So that's what this is all about. The Taylor series, essentially, the first order approximation is just this xc, which is just a line, right? Just this, the slope at 0 of the sine function is xc. And then you're adding these higher order correction terms to make it bend like the sine function does. And so what you want to plot here is this, you're going to take this interval and numerically you're going to chop it up into a bunch of little subintervals. And you're going to go like 0 to h, 0, like if this is width h, your plot is going to be the first point will be the integral from 0 to h, this difference. That's going to be the error under the curve between 0 and h. That's what you're going to be plotting. How much error there is. Maybe I can make a little bigger. Make this a little bigger. So if you've got and then you have some approximation, maybe it looks something like this, I don't know. So there's sine h. What we're after, right, is this is the error between the Taylor series, the truncated Taylor series approximation and sine of h, or sine, just the analytic function sine.
right. So when you define the error, you put the error under an integral, and when I evaluate that integral and do the difference for them, I just come out with 0. But are you meaning in that integral that you really just want to break it up into smaller pieces and do it like a numerical integration?
There's no numerical integration yet. What I'm saying is, you see how this integral has there's an indefinite xc in the limit of the integral. So what I'm saying is that the error at xc is, so let's say xc, for example, is this value here. So e of xc, if this goes up to here, e of xc should be this area. That'll be the number e of xc that you'll plot. And then you do it for the next xc. Maybe it's 2xc and then 3xc, and you're going to get a whole bunch of numbers that are adding up this error as xc gets bigger.
I think it's worth mentioning that this problem has changed. This is one of the ones that someone
yeah, exactly.
changed.
So I think on Wednesday there was some questions, and I went in here and fixed it up a little bit to make it a little more precise. Okay, so that's basically going to give you a plot. You know, this plot's going to maybe look something like, I don't know, maybe it'll look something like this, right? where this is going to be E of C. This is going to be that guy. And then what you do is you say, okay, well, like this is what we do in finite elements, right? We create some approximation, and then we introduce another approximation on top of that approximation, which comes from quadrature, because we can't actually evaluate, we're assuming we can't evaluate integrals exactly. So I take this guy and I replace it with this approximation, and then you compute another error, which maybe is a little bigger. I don't know what it'll be. Maybe let's say it's like that, right? So this is E of C. This is E N. And you're going to have one for each N. So if it's a 1-point rule, maybe it's really big. And then a 2-point rule should be a little smaller, E2, and so on, right? And then what you're going to do is you're going to take the difference between these guys. And that's going to be your final plot for each N, which is the error, the difference in the errors. And this allows you to study the buildup of error in your approximation. And you can see specifically, for example, what a Taylor series expansion does analytically. You'll be, I mean, I would even encourage you guys to keep adding terms. It's kind of cool to see how a Taylor series expansion works, how it snaps to the function, no matter how far away, no matter how far, you know, the radius. What does anybody know offhand what the radius of convergence of a Taylor series expansion of the sine function is?
Infinity.
It's the entire real line. So no matter how far out the sine function goes, you'll get all these polynomials that'll just magically add up to the sine function as you add terms. It's really cool, right? So that's a fun animation all by itself. But the Taylor series expansion is so fundamental to everything we do in applied math. And all numerical methods, if you look hard enough, you can find their origins in Taylor series types expansions. So I want you to understand that, you know, just through looking at it, like seeing how it behaves. And then, so that's step one. And then it's like, okay, well, if this is my model, if this guy's my model, let me do numerical integration on top of that and see for different integration rules. You should also be able, for n equals 1, the error will be pretty big, but if you increase the n, you should drive the error to 0 again. So you can control error in 2 places here. And this is in numerical methods, there's often many sources of error. And so having a really detailed understanding like this is significant. So this is a really, if you play with this one and kind of enjoy the process, you'll learn a lot about all these objects you may have been talking about. Like, you know, I remember learning Taylor series expansion in, you know, like your first calculus courses, but I don't remember having any understanding really of how it behaved or what it did or, but when you see it, it's kind of incredible, actually. And this is like one of the real foundations, right? The fact that we can take any continuous function and approximate it to any order of accuracy with polynomials is the whole reason we do polynomials in finite elements. So it all
is that equation specifically for sine?
Yeah, exactly. So in general, the Taylor series expansion is going to have a term for xc, xc squared, xc cubed, xc to the 5th, and then some derivative information. For every analytic function, if you go look them up, you'll find their Taylor series expansion.
Gotcha.
Sines, cosines, tangents, exponentials, whatever you want to look up. You can just write down their Taylor series expansion. This comes from what's called a Maclaurin expansion. Anyway, this idea that functions can be approximated with polynomials is a big deal. And you've been taking it for granted for a long time, and it's time for you to understand what that means.
Mike, can I ask you a question that might be a little bit of a digression from the exercises, but it's related to this?
Go for it. Yep.
So I want to understand how it is that your choice of your shape function contributes to things like locking. So why is it if you have a higher order shape function that your propensity for locking would go down?
Okay. Let's see. What's the best way to answer that?
I mean, I'm assuming it's related to this same thing, right? That your higher order shape functions have less error.
So here's the one way to think about it. What locking does is it essentially means that you're solving a problem that you didn't know you were solving. So we call locking like a parasitic phenomena, but one way to think about it is it actually changes your boundary value problem. So when you compute with finite precision, you're not actually solving the problem that you thought you were solving a stiffer problem. And so, okay, great, fine. So we're solving a stiffer problem. That stiffer problem is going to have a solution, but no matter what, it should be approximated better and better with higher and higher order polynomials. So I guess.
Hold on. So you're saying that when you're in your approximation space and you're using polynomials, it causes the problem to be stiffer than it otherwise would have been?
What I'm saying is you have this locking comes from like an incompatibility in the differential equations where if you had an infinite dimensional space, you would have enough functions to like overcome that incompatibility. But when you go to a discrete setting, these inconsistencies are exaggerated and you can't overcome them. And what happens is you get objects that are overly stiff. So that's a different problem that we're not prepared to talk about yet in terms of exactly the phenomena behind different kinds of locking and where it comes from. But okay, let's say there is locking. What that means is, in some sense, just in the discrete setting, you're actually solving a different problem than you thought you were solving, one that's stiffer than you thought you were solving.
Meaning that the HK problem, so assuming the HK is your real space and CK is your approximation space, so meaning that HK isn't as stiff as CK. That's essentially what you're saying.
Well, what it means is if you had an infinite number of functions to deal with, you could overcome this problem, this incompatibility. But when you go to a discrete space, you just don't have enough information in order to deal with that incompatibility.
So then could you enrich, like for any given problem, is there a set of potentially unknown enrichment functions that would?
Well, you can
make
always
the
just throw
locking
more.
zero?
I mean, every problem in locking is overcome as soon as you enrich the space. If you refine, it goes away. Every locking problem that there is goes away if you create a bigger approximation space. The point is that then it becomes really expensive to solve a problem that you should be able to solve with like, you need like 100,000 elements, whereas you should only need like 10.
So then why is it that you can just magically handle it with your quadrature?
Because oh boy, that is such a great question.
I'm happy I made your day.
Okay. Okay, wow. That is such a tempting question, Curtis. I don't even know what to do with myself.
Well, I watched a lot of YouTube videos about quadrature the other day trying to figure this out. So,
Amen.
Okay, so let me think. How do I? This is always. How do I answer this question in 90
well,
seconds?
can we just do like a wave equation and show, like, why can't there be a simple PDE that we know the analytic solution to, and then show how, you know, the certain approximation space would cause locking, and then integrating it differently would make it go away, right? Because that would make it all of a sudden intuitive.
Could someone repeat
Okay.
the question by any chance? I'm not sure if I heard it correctly.
Okay, the question is, we're talking about locking, which Curtis he's gone off the reservation, which is okay.
Yeah, but don't let me, I don't want to digress the rest of the class who
The
wants
problem
to
is it's
understand
so, I mean, this has everything to do with what you're learning. So anyway, locking means that when you're in the finite dimensional setting, you have the wrong solution spaces. Right? So you're like looking in the wrong space. And so you'll never find the right solution. And what this leads to is very stiff response. And this only happens in the finite dimensional setting. And so the question is, how do you overcome this? Well, you can always just make the solution space bigger and bigger and bigger. And as you do, your approximation will get better. But practically, that's not what you want to do because it takes a lot of compute time that you shouldn't be spending. So another way to deal with locking, which seems completely unrelated, is to pick a specific quadrature rule. Okay, now quadrature. Where does quadrature come from? Let's think about Gauss quadrature. You have these mysterious points where if you evaluate some function f at those points times some mysterious weights, you get some order of accuracy. These zeros are actually the zeros of a very specific orthogonal set of polynomials called Legendre polynomials. And what you can show is if you take the Legendre polynomials and you want to interpolate some function f with Legendre polynomials, if you evaluate the Legendre polynomials at the zeros of these polynomials, you get some optimal interpolating approximation to f. So what quadrature really is what you're saying is if I evaluate at these points, somehow I'm inheriting the approximation power of this Legendre polynomial. And the number of points dictates the degree. So what you're actually doing with quadrature, by changing quadrature, you're actually changing the solution space. It's a backhanded way to change your solution space. Because you pick a quadrature point, but those quadrature points come from specific interpolating polynomial spaces. So that's why reduced quadrature that's why it's like magic, right? Because it seems completely unrelated unless you understand the relationship between the interpolation problem with certain orthogonal sets of polynomials and quadrature points. In fact, if we look at the next lecture,
But see, Mike, the Legendre polynomials, the nice thing is with the shape functions we choose, we get exactly 0 error until we reduce the quadrature for locking, and then it has error, right?
it should be the opposite. You change the quadrature, it should help with locking.
No, I'm pretty sure that when you have, so maybe I'm misunderstanding something. I thought that fully integrated elements, you select your quadrature points so that you get 0 error on your shape function, right? But then when you reduce it.
No, there's never 0 error. The integrands are not polynomials in finite elements, first of all. But anyway, if you want to learn more about Legendre, I just got done. This is for next week. We're going to talk about this and how the zeros of these, you basically take the monomial basis and you orthogonalize it and you get all these amazing polynomial bases, and these polynomial bases are the basis for all quadrature schemes, and it comes from polynomial interpolation is where it comes from. Okay, let's not spend any more time on that. question. Sorry, Curtis, we're gonna come back.
That's okay. I'm sure it'll come up every other class or so.
But the point is that quadrature is really interpolation. That's what it is. So when you pick quadrature points, you're picking an optimal set of points where in a particular polynomial space, you get some kind of optimal approximation. So if you change the number of points, you're changing your space. So your finite element space could be cubic polynomials, but you could pick a low order quadrature rule that actually means you're in the quadratic polynomials and you don't even realize it.
Yeah, that's what I was hitting at. So it no longer matches the polynomials you chose for your shape functions exactly, but okay.
So think about 1-point quadrature. All 1-point quadrature you could have 10th order polynomials on an element, but if you evaluate it at 1 point, all it can see of those polynomials is the constant. Right? All it can see is the constant term. So if you look at a polynomial as a Taylor series expansion, all you can see if you pick a particular quadrature rule is a certain amount of that information. So you can play with quadrature on different terms of a differential operator to massage the space to be a space that maybe you don't even know how to construct with polynomials. But you can get a quadrature, for example, on certain parts to reduce the locking. Okay.
Thank you, Mike. That's very helpful. I'll be thinking about that.
Great question. No, it is an awesome question, Curtis, but we just need a couple more of these, couple more weeks before. I mean, this is the cool thing is like all this stuff is like, it's all related in a very beautiful way. And there's really only a couple things you need to know. Okay, let's open it up again for other questions. Okay, I'm gonna, does this mean there is no other questions?
Looking at the homework and thinking about it.
Okay.
So Mike, can you explain how quadrature averaging, if there's no other questions, from a functional analysis point of view, like you've been doing earlier, like how that represents a slightly different space in your approximation?
Well, I think that's the one I did where, let's say you pick your approximating space to be 10th order polynomials. Then let's say you decide to use 1-point quadrature. Well, 1-point quadrature certainly isn't enough. There's not enough points there for you to actually reproduce 10th order polynomials, right? You're not getting enough information. You're only evaluating things at a single point. So you have exactly one parameter, right? So you need enough points that you can reproduce at least up to the dimension of the space. So 1-point quadrature, all it can see is the constants in that 10th order space. So numerically, even though you've written down on a piece of paper that you're using 10th order polynomials, and you've told the computer to use 10th order polynomials, as soon as you said, I want to use 1-point quadrature, the reality is that you're using constants because you're only evaluating the problem at the quadrature points. You don't have infinite precision. You can only get enough information out of the space if you have enough points where you look at the space.
Right, but it's still, yeah, and it's not the same as just reducing your shape functions because it is an average of those shape functions, not a reduced shape function. Right?
There is a way, there are some papers that relate different quadrature schemes to different kinds of mixed methods. quadrature is like putting some kind of like some constraints on the space and changing it.
I feel like you're baiting me into another question, but I really don't want to digress the class too much. So.
Wow, I'm surprised there's no more questions on the homework.
I have another actually, as I'm
Okay,
working on
great.
number 4, trying to redo this with the updated problem. And I guess I'm just running into trouble figuring out how am I supposed to plot the second part, the approximate integration error, when the Gauss-Legendre quadrature is just kind of has that set -1 to 1, and there's no continuous points in there. So I'm just trying to figure out how to plot that against
Oh,
something
you mean
that
like moving from -1 to 1 to the 0, 1 interval?
is that what we're supposed to do? Because I guess I'm trying to figure out a way to get like the Gauss-Legendre at multiple points within that 0 to 1 interval, but
Oh,
is
no,
that
no.
not
Yeah,
necessary?
you're overthinking it.
Okay.
Let me show you. So you have if you want to go from -1 to 1 and you want to do a change of, this is just change of variables, which is why
Right,
it's a problem.
right.
So change of variables into 0 to 1. Then you need to come up with, so this is, we'll call this x of xc, let's say. Okay, so
Mike, would that be 0 to c in this case?
yes, thank you. So let's call this, let's call this xc hat, or c bar then, we'll call this, or let's call this, sorry, x. And then we'll call this xc. Okay, yeah, so we need to write down this equation. This is just what's called an affine transformation, so it can be represented as a xc bar plus b, and we have to determine a and b. So how do we determine the unknown coefficients a and b? Well, we know that by the change of variable formula that x at -1 is equal to 0 and x at +1 is equal to xc. But this is two equations. There's two unknowns. So you should be able to create a little linear system for a and b, where the first equation is x at -1. So you plug in -1 here, and it gives you b minus a, right? So it's -1 plus 1 in the first row. Then x of 1, and that's equal to, so over here you have 0, and it's going to be c. Second equation is x at 1, so you plug in 1 here, so that's a plus b, 1, 1. And then you invert that matrix to solve for a and b, and that gives you the change of variables formula, and then you just plug in your quadrature points into the change of variables formula to get their new position. So you can just write a little algorithm very quickly to do this for any value of xc that you're using in this error plot.
Okay.
And I remember, I'm not ashamed to admit it, that when I was an undergrad engineering student, I would have struggled even writing down a 2x2 linear system for axc plus b. So don't be ashamed to ask me more about this. Two equations, two unknowns. Anyway, this is just computing. So you're computing the coefficients of a linear, right? Of a linear polynomial. This is the constant term. This is the linear term, linear coefficient. And so what you're going to do is you know the quadrature points between -1 to 1. Before you use them, just map them through this function. So you get them between 0 and xc. And then the weights just stay the same.
So I'm actually kind of lost. You're doing problem 4, but I don't see how anything that you just did related to problem 4.
Okay, so the connection here is we need to do, where is it? Let me erase this. You see this here? Here's a quadrature rule. This quadrature rule is on this interval, because that's where we're evaluating the sine function.
Eric, a way to think about it is that, like infinite elements, right? You can have a mesh where you've got elements wherever they want to be in Cartesian space, right? They might be off somewhere like, you know, at 1 million or something like that. And we've defined Legendre quadrature in these quadrature schemes on a different domain, like from -1 to 1. And so the change of basis is that you essentially are taking this function from whatever space it was in down to that -1 to 1 space and integrating it there. And that's,
remember, you're doing numerical quadrature to replace this integral. But this integral isn't from -1 to 1, it's from 0 to xc. So you have to take the points that originally were, you know, here, and you have to map them into a new interval 0 to xc. And that's what we're figuring out.
And then do you substitute that transformation, that change of variable, into the sine? So it becomes sine of
so
that.
what you could do, yeah, exactly. So you have 0 to xc. We have sine of, how do I write it? X dx. That's the first part. That's just a standard integral where now this one, let's just work on this one because it's the same thing for both. But so when you go to do, well, no, you're just going to evaluate this at a bunch of points exactly. Okay, so let's not worry about that. But when you go to this guy here, right, xc I wi. Let's say that this the original coordinate system, let's say it was, let's call this xc, and then let's call this guy maybe, I don't know, let's not do x because that'll confuse things. Let's do it xc bar. Let's call this xc bar. So the reality is that this is xc bar, right? And then so this is this guy, let me, xc bar of xc I wi. You see that? So you plug in xci into this mapping, it returns, it takes like this point. This point's xci, so there's xci. You plug it into this mapping, it returns maybe this point, which is this guy, and then you evaluate the sine function there.
Gotcha.
So that makes sense. What was the H on sine?
Yeah, so somewhere in my notes I wrote about this. Where's H? This here, this little guy. This is that what you're talking about? This superscript. Whenever you're in numerical methods world, or the theory of approximation, or numerical analysis, whenever you see a superscript H, it's just conveying to the reader that this is an approximation.
Okay.
Yeah, and it comes from the fact that in theory, in a lot of the theory, when they take a domain and they chop it up into a bunch of little elements, they'll say they have width h. And so it's come to denote like a discrete approximation. Yeah, so it basically has no real, it's not a variable. We haven't defined h anywhere. It's just conveying some information to the reader about the object.
That makes sense. Thank you.
Mm-hmm.
Dr. Scott, I have a quick question. Could you talk a little bit about number 9? And I'm kind of curious what you mean by specifically characterizing the null space of the semi-norm.
I was wondering. I thought it. I was wondering when someone was going to. I love this question, but it's probably the most theoretical question on the homework. So I thought maybe people just hadn't gotten to it yet. Oh my goodness, what is there to say about this one? Okay, so we talked about semi-norms. Here we go. Here's a semi-norm. It's just like a part of the full norm. So this would be the H1 semi-norm. And it's not a full norm because we remember the full norm would have U squared also in there, right? So that doesn't have that, so it's not the full norm, which is why we call it a semi-norm. Now, null space, what is that? Like, first of all, like, man, it's hard to work with something like a null space if you have absolutely zero intuition of what it is. Does anybody have any, like, intuition? This is what I'm trying to help you build here of what a null space is. I mean, I give you a mathematical definition in the notes, but
That was in linear algebra like 3 years ago, so I'll have to look in the textbook that I had.
yeah, that probably won't be helpful.
So
probably just be some.
Yeah, it wasn't.
So Dr. Scott, correct me if I'm wrong, but it's the null space where you're finding solutions that yield 0, but one of the components is non-zero. So you're trying to find non-trivial solutions that map to 0.
Yep. So let me unlock some intuition. Let's talk about, I use this term rigid body modes. Does everybody know what that is? Okay, a rigid body mode would be if I had a structure, let's say I had a perfect square, and I mapped it into a new configuration where all I did was spin it, let's say 45 degrees. How much energy, is there any, so let's say this is epsilon, there's 0 strain initially, right? If I rotate an object 45 degrees, do I induce any strain?
No, you don't. So
the strain remains 0. Since energy, the internal energy is a function of strain, that also means that there's no, even though that there has been a change in configuration or position of the shape, it wasn't associated with any change in energy in the system. These are both 0 energy systems. But this transformation, this is just an affine transformation, okay? So it's also written like AX plus B, okay? So what this means is that if you have a stiffness matrix, K, and you multiplied it by some vector, some linear vector, let's say A, B, and then a bunch of zeros, and you put zeros in here, that even though this vector represents a rigid body motion, but when you multiply it by the stiffness, it should be 0, right? Because there is no energy associated with this particular vector. That's a rigid body mode. So a rigid body mode is all of the functions that take a structure and rotate it, translate it. That's really it. In 3D, there's 6 possible rigid body modes, but it's really just all the linears, all the linear polynomials are the affine transformations. So any linear polynomial should be mapped to 0. So the null space is the space that contains every possible function that maps to 0. So in the case of a structure, it would be of dimension 2 in 2D. right? I guess in 1D it would be dimension 2, in 2D it would be dimension 3, in 3D it would be dimension 6. But it's just the dimension of that linear polynomial space. Okay, so now think about what that means. Why? So we have non-zero vectors that are mapping to 0. We know if that's the case that we cannot invert K, right? K is not invertible if this is the case. If the null space has something in it, you can't invert the matrix. Okay? And so if you can't invert the matrix, you can't solve the problem, which means a big part of structural modeling oftentimes is let's remove the rigid body modes. But mathematically what that means is I need to change this problem so that rigid body modes aren't possible. That's the same thing mathematically as removing the null space of the operator. So that's the relationship between the intuition and the mathematics. Now this right here, this H1 semi-norm, this semi-norm is equivalent to what we call strain energy. Do you see this? This is nothing more than epsilon squared, strain squared. It's the derivative of u. But what's the problem here? What if you take a function and you differentiate it? It blows away certain terms, right? Like certain constant terms. It just blows them away, and it can't see them because you've differentiated away the constants. So it can't differentiate between the solution u and the solution u plus a constant. Those constants, those are the rigid body modes, that's the null space. So every time, and this is nothing more, this is structural mechanics right here, right? This is quasi-statics, linear elasticity is what this semi-norm is equivalent to that in 1D. So mathematically, we don't care about the application. We just care about the structure of the operator. But it's helpful to know that where this operator comes from. So when you're looking at a semi-norm and you want to characterize its null space, first you look at the differential operator. This tells you right away, the order of differentiation should tell you right away what are the things that are being blown away that you can't see. In this case, it's all the rigid body modes. So the null space in 1D will be let's see, it's just the, no, I'm wrong, it's just the constants. So it's just going to be dimension 1 in 1D. It's just going to be the constant term that it can't differentiate between. A constant translation of the object in 1D. So in this case, the null space is a one-dimensional space contained with all the infinite possible constants. Okay? And so because it has a non-zero null space, you can't invert it. So what we normally do is we'll add boundary conditions to this in order to get rid of the null space. Okay, so yeah, so that's how you characterize the null space. And then defining a semi-norm, you just use it's the same exercise you did with the inner product, basically. Is it a linear operator? Well, just run through the definitions and see if it satisfies those.
That was super helpful. Thank you, Dr. Scott.
Okay. All right, well, we're over time. That was good. It's nice to get away from the rigid lectures and just talk about some of these things. Okay, I'll see you guys on Monday.
Dr. Scott, there was a question in the chat.
Okay, the chat. Yeah, I've found that I can't monitor the chat on top of everything else. So I usually just turn it off, but let's see. Chat.
I was just asking if I could ask a question, actually.
Oh, Mike. Hey.
Yeah. Yeah, I'm here sometimes.
Yep. Okay. Just,
all right. This goes back.
Just stay on the call.
What's that?
Yeah, just stay on the call, and
okay.
I'll answer it.
Well, other people might be interested. It's relevant to the class.
Okay, then go ahead and ask it, and everybody else that wants to drop off can.
want. So you were talking about the relation between H spaces and C spaces. And so H1 is in C0 and 1D from the Sobolev embedding theorem. And H1 was not in C0 for, say, 2D.
Yeah, that's right.
Right. And so that's an interesting thing. So that's telling me that basically, say, elasticity, when you think of it in terms of minimizing energy, naturally lives in H1. And so it's telling you that solutions to elasticity exist that are not even C0.
Yeah, that's exactly right. That's exactly what it's saying.
And so then given that, why do we, for example, when you're going to say higher continuity, right? Why does higher continuity help you when you're trying to approximate a space which isn't even C0?
Yeah, so that's a great question. That was an important, surprising result in the beginning history of IGA, where there is this idea that, well, if I have a rough function, what's the best way to approximate it with polynomials? And your intuition leads you to say, well, the polynomials shouldn't be too smooth, right? It turns out that with splines, you can actually show that smooth splines are actually optimal per degree of freedom, even for rough functions. So there's a paper called Nwitz, Soup Ints, and something. It's by John Evans and Hughes and Babushka, which this is where that is, you can actually show that of all possible spaces, including, the spline spaces, that in some sense these K spaces, these ones where you have optimal smoothness, so C to the P minus 1 for a given P degree space, they're actually optimal even when defining functions that are rough.
Interesting. That's pretty cool. I'll look that up. Thanks.
Yeah, there's some weird things, right? Like about polynomials and their ability to approximate in the limit that are not intuitive.
Who was the author of that paper again?
John Evans is here. I put it in the chat. So John Evans is the
see it
first
now.
author. Yep.
Thank you.
All right, can I ask one more question?
Sure.
Same topic, it's related. So like, you mentioned in the notes that the natural space for, say, solving elasticity is H1, right? Because you have this broken semi-norm here that's dividing the energy.
Right.
But you can also, of course, you can write things in weak form as an energy principle or in strong form. So when you have elasticity in strong form, you have two derivatives. And so you need, that sufficient continuity. And so I guess, is it true, the following statement, that depending on how it seems kind of funny, because depending on how you write the problem, you either need C1 or C2 continuity, or you need H1.
Yeah, but they're actually, here's the thing that's even crazier, Mike, is they're actually in the infinite dimensional setting exactly equivalent.
Okay.
And what that tells you is that in the infinite dimensional setting, you have enough C2 functions that you can approximate the solutions in H1, if that makes sense. There's an equivalence there.
Yeah, I mean, I think that intuitively makes sense to me too, because if you think about the weak form, right, you do like, for all functions in space. And so if it's infinite dimensional, they kind of have to be equivalent, maybe. That's my intuition there.
Yeah, so that equivalence of strong and weak only holds in the infinite dimensional setting.
Yeah, that makes sense. Okay, got it. So
yeah,
even though I need two derivatives for my strong form, I'm not even C1.
Exactly, which is why, like, yeah, I mean, that's why, yeah, that's the problem, is that for a lot of these strong form boundary value problems, you have really higher order differential operators, and for a lot of sets of boundary conditions and things, you can't even find the solution in classical spaces, right?
Mm-hmm.
So you have to look in weak spaces, and the only way you can do that is by introducing an integral, and so that's why you do integration by parts.
All right, I appreciate that. Thanks.
Yep.
Mike, I think I've posted the link to that paper you were referring to.
Yeah,
in
thank
the chat.
you. I appreciate it.
Do people have a preferred way to plot? Are they doing everything in Python, or MATLAB or
I would imagine most people probably do MATLAB because they probably know that.
yeah, that makes sense.
Okay, thanks everybody. It was a great conversation. I learned a lot as well. I appreciate it.
Thanks, Mike. I appreciate you talking us through this stuff.
Okay, we'll see you later.
Thank you. See ya.
Bye, everyone.